Thanks, everyone. I'm here to welcome you to SC14. My name's Ian Buck. I run our accelerated computing group. I joined Nvidia about 10 years ago and was the inventor of CUDA. And since then, I've had the opportunity to watch it grow from that first announcement actually at supercomputing to here. Just the last year has been an amazing year for us. We were here a year ago announcing the fastest supercomputer in Europe and the fastest, newest GPU, the K40. Since then, there's been a ton of activity around GPU computing, including the world's fastest enterprise supercomputer at ENI. We announced NVLink at our GTC conference, and there's been some amazing activity in machine learning with our new cuDNN machine learning library and the image recognition competition. Just this activity around machine learning is particularly amazing. Of course, what's made the GPU computing so successful has been what we've been building for almost 10 years now with Tesla. Tesla is our platform for computing. It's not just about the accelerators. We certainly build some of the world's fastest accelerators, which we'll talk about. But it's also about our interconnect technologies within the node, things like system management, and all the things you need in order to build a GPU-accelerated data center or supercomputer. And of course, as part of that, there's also all the work we do with the developer community, in compilers, in profilers, debuggers, and of course, libraries. This Tesla platform is important not because of the technologies that are in it, but because of the partners that build their technologies on top of it. Folks like IBM and Cray and HP and Dell, or in the cloud with Amazon. But the developers like Alinea and PGI and libraries like Kitware and MATLAB. Building this platform has made us, let us achieve this level of success, and we have a lot of technology here in our booth and of course across the show of examples of people using the Tesla platform to really accelerate science and discovery. Of course, it's also an open platform. Open in there's lots of different ways to program it, whether it be the libraries like our machine learning library, cuDNN, compiler directives, or directly explicitly in programming languages like C and Fortran. It's also an open platform because we target lots of different architectures. We, of course, support x86, but with our partnership with IBM, we now support Power, and you can get full support of CUDA and our platform on the Power architecture. And earlier this year, we announced ARM as well. So now we support both x86, Power, and ARM. And it's really it's evolved into this wide breadth of both developer solutions and hardware platforms. This diversity and this breadth and this depth have not gone unnoticed. And if you may have noticed on Friday, there was a new announcement. The U.S. and the U.S. Department of Energy has decided to build 2 of the new flagship supercomputers as part of the Coral collaboration. Coral is the collaboration, of course, between Oak Ridge National Labs, Argonne, and Lawrence Livermore. On Friday, 2 supercomputers were announced, the Summit supercomputer and the Sierra supercomputer. And really, it's a partnership for science, of building these supercomputers and the science that they can achieve. They're truly amazing. It's 100 to 300 petaflops of peak performance and over a 10x acceleration in the kinds of applications they're going to run. And of course, this will be built for 2017. This is really a major step forward in our path to exascale. As you can see, we're right on the cusp. We're getting there at 300 petaflops. Just to put that number in perspective, each one of these nodes is about 40 teraflops of performance. If you took just 4 of those nodes, they would actually be on the top 500 today. They're extremely energy efficient. These systems will actually, the Summit supercomputer will actually fit in the same power envelope as Titan. But and to put the petaflop number in perspective, of 150 petaflops, that's about 3 million laptops. If you took those laptops and stacked them one over another, you'd actually leave the Earth's atmosphere and be in space. It is a big number, and I can't wait to figure out what exascale means in terms of laptops. So I can tell you more. Of course, it's not about performance. It's really about the science and what these systems are, what they're built for, what the kind of science and discoveries that their goals are to achieve. Now, I could tell you about those things, but we thought it would be better to actually have the people who are building and going to be running and operating these machines come up on stage and tell you what it means to them. So first, I'd like to invite Jeff Nichols, the Associate Laboratory Director for Oak Ridge. Jeff, can you tell our friends what Summit means for you guys?
Sure. Thanks, Ian. So we're excited about supercomputing, and in particular, we're excited about supercomputing with the accelerated node technologies that we've started back in 2009. So let me get right to it. If you can remember back in 2009, Jensen, I stood on the stage with you in San Francisco, and he called me out on the stage, and Jensen said, what are you guys going to do with the GPU technology that we're actually building together? And I said, we're going to build the world's fastest supercomputer. And that was in 2009 in front of a gaming community. 3,000 people were at that gaming conference, and they were all looking at me through red and blue glasses. And they thought I was a little bit crazy, and they thought I was actually going to build the world's fastest Halo system, right? So that was an interesting introduction to supercomputing with Nvidia. But, you know, we actually went on to build Titan with these types of GPUs, these accelerated node technology type systems. And so what I'm here to tell you today is that we're going to take the next step. We're going to go from Titan at 27 peak petaflops with about 9 megawatts of power, and we're going to go to 10x that performance. We're going to go between 27 peak petaflops, 5 times that technology is 150 petaflops of peak performance. And to be honest, if I'm serious with you, I want 300 petaflops at Oak Ridge National Laboratory. So we're going to figure out how to get there. And we're going to do it within that same power envelope of 10 megawatts of power. So we're excited about Summit, which is the name of our next machine, 5 to 10 times the power of Titan in the same energy envelope as we have today. That's significant. And then we're on our way to exascale, and we're going to get to OLCF5, Oak Ridge Leadership Computing Facility, in that 20 megawatt window. What makes it unique? There's a lot of things that we can tell you today, some things we can't. 3,400 nodes. For an application developer, having a few thousand nodes as opposed to a few tens of thousands of nodes is a big difference. So a few thousand nodes at 40 teraflops of performance and large shared memory infrastructure is extremely important and something that we all want to have at our fingertips when we talk about a quarter of an exaflop machine. And so that's a big deal. And so what makes it possible? What makes it possible for us to have 40 teraflops for each node? It's the IBM performance with their CPU systems and the Nvidia GPU performance that gives us that 40 teraflops of peak performance. It's NVLink, which was mentioned as that technology which has been developed in order for us to have huge amounts of shared memory in each of those nodes. And you put a few thousands of those nodes together, and you get the kind of performance that we'll have with Summit technology. And so we're very excited about having a few thousands of nodes at 40 teraflops each. Each of those nodes has over 512 gigabytes of shared memory, and we also have burst buffer memory. We have over 800 gigabytes of NVRAM, which can be configured. And so this is extremely powerful and exciting to us as we move forward. So Ian said we're going to use these things to do science. And we're already doing great science at the laboratory with Titan. But this allows us at 10 times the performance to do 10 times as much science as we could possibly imagine. The other thing that it allows us to do is not only do the CPU-intensive types of calculations that we do today, but it allows us to do that data-centric types of modeling and simulation that we would like to do. So it allows us to ingest data at unprecedented rates. It allows us to take data from our experiments, from our spallation neutron source. We can take that data in, and we can actually use that data in our modeling and simulation calculations in order to predict the performance, to predict the experiments that are actually going to be done at the spallation neutron source. So we actually do things in the material space. We do things in terms of looking at complex models of earthquake simulations. We look at climate science. If you think about what climate science is today and how we actually do the modeling and simulation with regards to climate, we have to worry about all of the modeling and the physics associated with the land, with the atmosphere, with the oceans, and with the ice. And this allows us to bring data in from the kinds of atmospheric radiation monitoring systems, the carbon dioxide systems. It allows us to bring the data in that would actually allow us to do the validation and verification of our models. Extremely important as we go forward, and extremely important as we increase the fidelity of our physics models in order to understand climate. Nuclear reactors is one of my favorite ones because today at Oak Ridge we have the Consortium for the Advanced Simulation of Light Water Reactors. And the whole reason for existence of that consortium and of that energy hub, that was the first energy hub that was granted by Ernie Moniz and the Secretary of Energy. That energy hub is supposed to help us to understand nuclear reactors and those reactors as a function of how they actually burn the fuel and actually generate the heat and make sure that we don't have lots of materials that we have to keep for long extended periods of time. So we want to make those reactors more efficient. And we can actually do that by building a virtual reactor. And we've actually put the first virtual reactor out on test stands with TVA and Westinghouse today. But this system allows us to have much more fidelity, more safety standards, to be able to get those models so that we can actually get them through the Nuclear Regulatory Commission and actually use them to extend the lifetime of our reactor fleet and actually generate new materials and actually make them more efficient, generate less waste, and actually be there for us as a people in the United States as we move forward and get away from the kind of carbon that we're putting into the atmosphere. So we're extremely excited about what Summit means and how the science that we can do will help benefit all of us as we move forward.
Thanks, Jeff. That's awesome. Next, I want to invite on stage Rob Neely, who's the Associate Division Leader at Livermore. Rob, you're new to GPUs, actually.
Yes, we are.
So why don't you tell us about what GPUs meant for you and why you chose them?
All right, sure. Thank you very much. So great intro by Ian and Jeff. Thank you for that. As Ian said, at Livermore, we are new to GPUs. I'll tell you what prompted us to make the leap for the Sierra system coming in 2017. Just real briefly, this is, like Jeff said, it's all about the science and the applications that we can perform on this machine. At Livermore, we're, along with our sister laboratories in the NNSA, responsible for the maintenance of the nuclear stockpile in the United States. This is ensuring that they are safe and reliable so that we don't have to go off and resume underground testing, and that takes a lot of horsepower. The applications that run on these machines, very complicated, large multi-physics applications. These are not codes that we can just decide to rewrite for some new architecture. So this Sierra machine and the Tesla framework that was described here is the first time that we've been able to look at accelerated computing as a way for us to have a natural transition from our application base into something that we feel can get us the performance we need. I'm going to compete with the band here, so the science we're producing at Livermore is a combination of very large-scale applications where we want to run on the entire machine, but we also want to focus on uncertainty quantification, using the machine to get the most throughput on tens or hundreds or thousands of jobs. Eventually getting to an exascale regime with, say, 100 or 1,000 high-fidelity three-dimensional applications running simultaneously to give us the uncertainties we need for the science. So, as Ian and Jeff pointed out, the thing that really sold us on making the jump to accelerated computing was this NVLink. This is just a cartoon of a node. You've got a CPU and an accelerated GPU today. There's that thin PCI Express bus that not all applications can take great advantage of GPU technology. What NVLink buys us is super high bandwidth memory access, coherent memory access, so that memory on the CPU can access memory on the GPU and vice versa. That, in combination with the software stack that's being developed, that's being co-designed with the Coral Consortium, Nvidia and IBM, it's really giving us for the first time a programming model that looks like something we can transition our existing code base onto these very impressive hardware with relative ease relative to where things are today. So a lot of this has already been discussed. The IBM Power architecture is going to be the CPU on the node that allows us a quick pathway to get high performance for the codes that haven't gotten to acceleration yet. These are very memory-rich nodes, as Jeff pointed out, 512 gigabytes on a node. The GPUs are just continuing to improve. The Volta in this time frame, I don't know what we can say about it, but very, very impressive technology, I'll tell you that much. As part of this RFP, IBM and Nvidia did a really outstanding job evaluating our benchmarks and giving us some promise that we're going to be able to achieve this 5 to 10x improvement in applications. And then again, cost competitive, energy competitive, inside a similar energy envelope to what we have today with our flagship system, the IBM Sequoia Blue Gene system. And one thing I'll point out here, we have a contract in place that's been going on for a couple months, starting to get this partnership rolling. The thing I'm really excited about, we're developing these centers of excellence at both Oak Ridge and at Livermore. We've got a 3-year runway now for this machine to hit the floor. A lot of time to develop. Not a lot of time to prepare our applications, but more time than we've given ourselves in the past, and we're partnering with NVIDIA and IBM starting now to help prepare our applications, to train our programmers, to train our domain scientists how to reason about targeting accelerated computing, and then getting the application so that when this machine hits the floor in 2017, we're ready to go with it. And I think that's all I'll say.
Thanks, Rob. So Rob and Jeff will be around later if you want to ask any questions. I want to continue to talk about our platform and some of the things that we're announcing that's sort of new to the Tesla platform. Both speakers talked about NVLink, and it's a very important milestone that we've and part of our platform roadmap. And they both talked to it. Basically, NVLink really allows the serial processor of the CPU to talk to the GPU at speeds unprecedented speeds that allows the GPU to access the bulk memory of the CPU at the same performance the CPU can itself. This obviously dramatically increases application performance, but it also really improves programmability and productivity of the developers, which is both speakers talked to, really important in their decision to go with GPUs with Coral. Of course, it wouldn't be supercomputing without announcing another accelerator. And just this morning, we announced the Tesla K80, the world's fastest accelerator for data analytics and scientific computing. It's actually a 2-GPU accelerator and providing aggregate performance of almost 3 teraflops, almost 5,000 cores, and a total bandwidth of over 480 gigabytes a second. Truly an amazing accelerator. In some of our applications, this is a deep learning neural net application called Caffe, almost doubling the performance when you run it on K80. Each GPU has 12 gigabytes of memory for an aggregate amount of 24 gigabytes, which is great for the big data applications. And of course, with GPU Boost, we'll actually dynamically optimize the power to spend power where your application's spending it, whether it be in memory bandwidth or in flops or in communication. A very impressive K80. We have it in our booth over here, and you can take a look at it and see what it's able to do. And K80, of course, is just another GPU on a long line of successful accelerators that we've been doing all the way back to the beginnings of accelerated computing. And we continue to outperform CPU-based accelerator systems, either in flops or in bandwidth. And, of course, in real applications, which really what makes them successful. I want to not only do we have the K80, but we also have a new capability of the Tesla platform, and that's visualization. We've now enabled our graphics capabilities of the Tesla platform, which has obviously been focused on computing for so long. We've enabled and focused on, for this show, on the graphics capabilities. Some of the science that's being done today is at a scale that's truly unprecedented. This is a chromatophore cell. It's a 100 million atom cell, and is actually the building block of photosynthesis. This cell is able to allow biology to convert light into energy. And understanding the biology of and how this cell does that all the way down to the atomic level is a really important scientific mission, so that we can actually figure out how biology does this, so we can actually turn around and do things like biofuels and carbon-neutral energy sources. Understanding things at this scale needs visualization. It's 100 million atoms. It's an extremely complicated model, and the only way to understand it is actually to visualize it and actually see it happening. We announced this morning a partnership with Kitware. That Kitware and Nvidia have partnered to actually accelerate visual analytics and rendering. And Kitware projects that their next version of VTK, called VTK-M, will achieve over 100x speed up of their visual analytics. Here at Supercomputing, we have some amazing visualization demos, actually running on real supercomputers. The P-Date supercomputer we talked about last year, they actually have the chromatophore rendering. You can interact with it in real time. A simulation of the Milky Way, which is actually a Gordon Bell finalist this year. You can actually see the simulation happening in real time on a supercomputer, streamed across the country, and in the case of P-Date, halfway across the world, here to supercomputing. And finally, of course, the HIV capsid, which is on the cover of Nature. Some beautiful renderings of actually what does the HIV virus look like? What is its structure? And understanding its structure allows scientists to really understand how it infects cells so that we can actually build medicine to intercept those active points. Amazing renderings, brilliant science. I encourage you all to come around the corner after the show and see some of it, or hear while you're here at SC. That concludes my talk. I want to welcome everyone to Supercomputing 14, and I hope you get to learn a little bit more about our platform for discovery. So thank you all for coming, and enjoy the rest of the show.